Hi everyone, welcome to new lecture by Togo AI Labs, Understanding LinkSAGE. My name is Aishwarya Kodamur. I am the co-founder of Togo AI Labs. In this lecture, we will be understanding LinkSAGE, LinkedIn's flagship graph neural network. So we will be covering the theory, math, and we will be understanding LinkSAGE by using a simple numerical example. LinkSAGE is inspired by GraphSAGE, a very popular graph neural network. So let us get started. Today's lecture will revolve around the research paper published by LinkedIn's researchers in 2025, LinkSAGE Optimizing Job Matching Using Graph Neural Networks. So, over the last 4.5 years, I have been researching graph neural networks, and this is one of the papers that inspired me. This paper, LinkSAGE Optimizing Job Matching Using Graph Neural Networks by LinkedIn's researchers, this actually adapts GraphSAGE and uses that on the real world job marketplace graph that LinkedIn uses with billions of nodes and edges. And there are some other specialities like, unlike the smaller graphs, this actual job marketplace graph is huge or gigantic in nature with billions of nodes and edges. And also the graph is heterogeneous, dynamic, and there are challenges like sparse engagement and cold start problem. So we will see how LinkedIn recommends jobs to the members by using LinkSAGE. And we will also see why LinkedIn chose a graph neural network based recommendation system to match job seekers with recruiters. So let us see. We will be first building a tiny job marketplace graph, and we will perform GraphSAGE aggregation on that graph. We will see how LinkedIn matches job seekers with recruiters, and also we will understand what were the challenges the researchers faced when they were developing LinkSAGE and why LinkedIn decided to have a graph neural network based recommendation for matching job seekers and recruiters. What were the challenges and how LinkSAGE solved those challenges. So this will be the main goal of today's lecture. Here on the screen, you can see a complex heterogeneous graph, a very small heterogeneous graph with different types of nodes and edges. This is an example of a job marketplace graph, the simplest example of a job marketplace graph. Here you can see there are different types of nodes, member nodes, skills, jobs, companies, positions, and titles. All these are the nodes of the graph. So this graph is the exact graph that is mentioned in the paper. So I decided to choose the same graph. And this graph is heterogeneous in nature, meaning there are different types of nodes and edges. Now, what are the possible edges in this paper, in this graph? Whenever there is an engagement between different types of nodes, we can say there is a formation of an edge between the two nodes. So when can there be an edge formation between the member node and a job node? What are the possible engagements? A member can either apply for a job, or the member can save a job, like, or even view the job for a few seconds and share the job to another member. All these are possibility of edges. So whenever there is an engagement between two types of nodes, then there is an edge formation, and our goal is to predict the probability of that edge formation. And here I said this is a heterogeneous graph, and this is the simplest possible job marketplace graph. In real world, the graph that LinkedIn uses is a huge, gigantic graph with billions of nodes and edges. So the size of the graph is very high, very huge, and there are different types of nodes and edges. Now, the third thing is, at every instance of time, new jobs can be posted and the irrelevant old jobs can be removed from the graph. So at every instance of time, there is addition of the new job nodes and the irrelevant old ones expire from the graph. And a member can join the platform at any instance of time, and the member can leave the platform at any instance of time. So if we have different instances of time like T1, T2, T3, and T3, then at every instance of time, there can be new nodes forming in the graph and old nodes exiting from the graph. So this means our huge heterogeneous graph is dynamic in nature. It changes with time. And imagine if a new user joins the platform, then there are no history of engagements. So how can we learn, how can the model learn the patterns of that a new user or a new node with no history of engagements or interactions. This is another problem. So I'll explain what were the recommendation challenges LinkedIn faced to recommend jobs to the existing members, and why LinkedIn needed a new graph-based recommendation model, and why they developed LinkSAGE. So the first challenge is the dynamic nature of jobs. LinkedIn connects over 1 billion users and jobs. So recruiters post new jobs dynamically, which means if we have different instances of time like T1, T2, T3, then at every instance of time, there will be addition of new jobs, and at every instance of time, when hiring is complete and when the job postings become irrelevant, then the irrelevant jobs will exit from the graph. This makes the graph highly dynamic in nature because at every instance of time, daily new jobs enter the platform and the irrelevant old ones expire from the platform and exit the graph. So this was the first challenge LinkSAGE had to solve. The jobs were highly dynamic in nature. The graph was highly dynamic in nature. Now coming to the second challenge, sparse engagement problem. Sparse engagement is, as I said, this graph is a huge graph with billions of nodes and edges. So that means there are a huge number of members on this platform, and there are many job postings every day. But imagine if I'm hiring for a role, I'll post a job and I will invite applicants. But imagine the number of applications for one particular job. Here, let us understand with the help of this small graph. We have one member here, and there are two different jobs. Now, even though we have billion members in this member nodes in this graph, the interaction with the job posting will be very less, which means if there are 100 job applications for this particular job, the total number of applicants, total number of members in the graph will be very high. There will be 100,000 total number of nodes, and there will be a very small fraction of applications. How this becomes a problem? A typical member in LinkedIn applies for a very few jobs, and this leads to limited direct supervision. So when we say engagement, we mean the direct explicit interaction between two different types of nodes, between the member node and the different job nodes. When we take a random member, they might apply for 5 or 10 jobs in a day, or even 50 jobs in a month, or maximum 100 or 200 jobs, or even 1,000 jobs in a year. But when we look at the whole graph, the total number of possible edge formation will be very high. It will be in the order of millions or 10 millions. So the actual number of applications is actual number of interactions for the edge formation is very less compared to the total number of possible edge formation. This leads to limited direct supervision, and even learning the patterns from the graph becomes very difficult. Meaning only a tiny fraction of the total possible engagements are formed in the graph. So in graph learning terms, this makes the adjacency matrix of the graph extremely sparse, meaning the number of actual formation of edges is very less, or it is a tiny fraction of the total number of possible edges. So this makes the model difficult to understand the patterns, learn the patterns of the graph, and recommend jobs to different members. So this is another problem LinkSAGE had to solve. Now the third challenge is multidimensional matching. This is the biggest challenge LinkedIn faced, what the authors mentioned in the paper, multidimensional matching. When we think about job recommendations, the relationship between a member and the job is not one-dimensional. We can think that, okay, the member can see different job postings and member can decide and apply for a job. So that is one-dimensional. We will think like this. But in real world, in real graph, this is not happening as a one-dimensional problem. So traditionally, the researchers thought if there is a job description, there will be text in that job description, and the members will be having certain skills and qualifications. So if the text in the job description and text in the member's profile, if these texts are overlapping and if it is matching, then recommending this job to the member or recommending this member to the recruiter will be the best thing. But LinkSAGE or the researchers in LinkedIn, when they were proposing LinkSAGE, they are proposing, they're telling that the job matching is not one-dimensional in nature, but it is multi-dimensional. So the third challenge, multi-dimensional matching, means if there is a job description and if there is the member's profile, then instead of simply matching the text we have to understand the different dimensions of the member's profile and the job description, and then the member should be matched with the recruiter. So it is not just the overlap between the texts. For example, the thing that I mentioned, job description and the resume. So traditionally, researchers believe that compatibility depends on single dimension, but here the researchers are proposing that compatibility depends on multiple dimensions. These can be the members' skills, titles, companies they worked at, and even the industries that companies belong to. An example is same job title can mean different things in different companies. For example, if I'm hiring an AI researcher, in my company, the role of an AI researcher will be reading the paper, understanding the papers, and helping the research team understand different research problems and solving them, and even learning new things. But in another company, the same title will be having different requirements and even different jobs. So same job title can mean different things in different companies. So traditional systems fail to capture this because they only see words. LinkSAGE solves this by considering different dimensions, by matching different dimensions. In LinkSAGE, this solves this by making each of these dimensions like skills, titles, companies, everything as a separate relationship type in the heterogeneous graph. So instead of simply matching the text, they are considering all the different dimensions by connecting the edges, by forming the edges and connecting different nodes. And they are considering each of these nodes as different relationship types and as different entities, and they are matching the job seekers and the recruiters. Now, next one is the cold start problem. I mentioned in the previous section, at every instance of time, new members can join the platform. There can be new job postings in the platform. The irrelevant jobs will exit from the platform, and even the members can leave the platform at any instance of time. So imagine here, if there is addition of a new member in the graph. If a new member is joining the platform at an instance of time, that new member will not be having any history of interactions. So without the history of interactions, how can we learn the patterns in this huge heterogeneous graph, and how can we recommend jobs to these new members? And if a recruiter is posting a new job, and if that recruiter or that company is not having any history of interaction, then how can we recommend members to that recruiter? So the addition of new nodes in the graph without any history of interactions, as this graph is highly dynamic in nature, this will cause a cold start problem. So this was another challenge LinkSAGE had to solve. Now coming to the last challenge, scale. Actual, this is just a simplified the tiny job marketplace graph. Actual LinkedIn's heterogeneous dynamic graph is very large scale. It is a very huge graph. It has billions of nodes and tens of millions of edges. So if understanding the patterns of a small tiny graph like this is very difficult, imagine how difficult it is working with a huge gigantic graph and using a model to train it. Earlier recommendation systems at LinkedIn relied on collaborative filtering and gradient-based decision trees with hand-engineered features. But these methods ignored the graph structure that inherently connects all the entities, because they might have treated everything as flat tables of users and item features. But in real world, it is not structured like a table. It is highly unstructured, highly dynamic, highly heterogeneous like a graph. So training a huge graph with billions of nodes and edges that changes over time. At every instance of time, new jobs enter the platform, enter the graph, existing nodes expire and they exit from the graph. Training on this huge dynamic heterogeneous graph was very, very difficult. And if learning patterns from this small graph is difficult, imagine how difficult it is to train a huge graph like that and learn the patterns. So in the paper, the researchers have mentioned it was impossible to form the adjacency matrix of the graph and train the GNN. So instead of using the adjacency matrix, they were using random samples of graphs, and they were training different samples of graph. Now let us see how we can understand this job matching by using this example graph. Here, instead of all these members, what I'm doing is I'm selecting this member 2 alone, and I'm selecting these two jobs, job 1 and job 2, and title 1, position 1, company 1, and different skills this member 2 has. So here is our selected graph. So this is a subgraph of our actual tiny graph, the subgraph of an already graph which is tiny. So here we have one member node, two skill nodes, two job nodes, 2 company nodes, and 1 title node. Here, member 1 is having skills S1 and S2. Member 1 is working in company C2, holding the title T1, and company C1 is offering another, maybe like I'm explaining this graph like this. Maybe company 1 is hiring for job 2, and our member M1 applies for job 1 and saves job 2. Let us make our story like this. So a graph being a collection of vertices and edges, here we have a simple heterogeneous graph with 1 member node M1, 1 title node T1, 2 job nodes J1, J2, 2 company nodes C1, C2, and 2 skill nodes S1 and S2. The possible edges in this graph, there can be static edges and there can be dynamic edges. So in this graph, the static edges will give us the background knowledge of this graph, and the static edges will help us to have a background knowledge of the graph, and dynamic edges will help us to understand the behavior of the graph. What are the possible edges that we can have in this graph? As I said, member 1 is having skills S1 and S2. So if we have an edge between member and skill, we can represent it as RMS, meaning this member has a skill. Similarly, if the edge is RMT, then the member has that title. RMC, meaning member works at a company. RJS, meaning job requires that particular skill. So here, the different edges that we have in this graph are RM1S2, RM1S1, RM1J1, M1C2. So if there is no edge between this member node and job 2 node, then if we can predict the probability of formation of edge between member node and the job node, if we can say, okay, there is 90% probability of an edge formation between these two nodes, then we can recommend this member to the recruiter, or we can recommend this job to the member. So our task in this, our research problem is predicting the probability of formation of different edges in this graph. This is one of the tasks. So the main thing is, in actual LinkedIn's job marketplace graph, it is a rich interconnected graph which is dynamic in nature, heterogeneous, very large, inductive. Inductive meaning if we are training the graph, then there will be some nodes and edges present during training. There will be unseen nodes also. So if our model can extend the patterns to the unseen nodes, then we can say that it is inductive learning. So in LinkedIn's actual job marketplace huge graph, it is a very large graph which is heterogeneous in nature, dynamic, and it is learning inductive. So the authors mentioned that, as I mentioned, this graph is very huge. It exceeds 10 to the power of 10 edges, making it impossible to process as an adjacency matrix. And instead of processing it as an adjacency matrix, the researchers were considering it as different samples, different neighborhood samples, and they were learning the patterns from those sample graphs. In our example, node M1 is applying for job J1 and is saving job J2. Now members and jobs connect to the attributes when there is an engagement. So what all can be the engagements? This applying or saving or liking or sharing or even viewing a job for a few seconds can be considered as an engagement. So in this, the two engagements are applying for the job and saving the job. The question is, how is the member matched with the recruiter? Here M applies to J1 and saves J2. So how is a member matched with the recruiter? Let us see. For that, we have to compute the similarity scores of J1, similarity scores of the edge between M1 and J1 and edge between M1 and J2. And by comparing those similarity scores, we can say, okay, there is higher probability of edge formation here, so we can match this member and the recruiter. So let us see how LinkSAGE is doing that. So now we are entering the math part of it. We are going to assign the initial features. We are going to perform GraphSAGE aggregation in this graph. Let us assign some initial features to all the nodes. So I am saying these are the random features that I am assigning. So it is not having any real meaning. But in real graph, these features will be carrying some meaning. So for example, if I am working as a data scientist, then my features will be having some meanings associated with my title, my company, my roles, education, and everything. So here, these are just random initial feature vectors I am assigning for easy mathematics and easy calculation. So this is not carrying any meaning in our example, but in real graph, it will be having some actual meaning. So these are the initial feature vectors. For member, I am assigning the feature vector, initial feature vector 101. For different jobs, J1 and J2, we have the feature vectors 0, 1, 1 and 1, 1, 0. for the skills S1 and S2, we have the feature vectors 1, 0, 0 and 0, 1, 0. Title is having feature vector 0, 0, 1, and let us only consider company C1. So job member is applying for job J1, which is offered by company C1. So let us only consider that now. Otherwise we can imagine. So let us only consider company C1 for easy calculation. So the initial feature vector of company C1 is HC1 of 0, which is 1, 1, 1. I am assigning these feature vectors initially. So these are arbitrary feature vectors, but they are fixed. Why I'm doing this is to make the math simple and clean. And this will be a very transparent, simple example. We'll be using just one GraphSAGE layer and the simplest design choices. Now we are going to compute the mean of the zeroth layer features. We have all the different nodes with initial feature vectors at layer 0 here. Now we'll be having one GraphSAGE layer. We will be calculating the mean of this feature vectors, and we will be using a simple combine step that averages a node with its neighbors. So why we are combining a node's own feature vector with its neighbors? It is because, for example, say you studied electrical engineering. So you have your friends who are working in electrical engineering domain, but currently you're working as an artist. So you will be having connections who are artists. So a person can have different types of interactions with different types of nodes. So your feature vectors will include all the meaning associated with electrical engineering as well as art. So by combining with self, we can aggregate the feature vectors of these two different domains. All your talents, all your skills, all your companies, education, everything. So this is just an example to understand why we are calculating the mean of all these nodes and why we are combining it with the self. So first step is aggregating neighbors of member M by using a mean. So which are the one-hop neighbors of member M? One-hop neighbor means the immediate neighbors of member node. Here the one-hop neighbors are S1, S2, J1, J2, C1 and T1. S1, S2, T1, C1, J1 and J2. These are the immediate neighbors or the one-hop neighbors of our member node. Now we are going to add the feature vectors component-wise. The one-hop neighbors of M are S1, S2, T, C1, J1, J2. So let us add the feature vectors of the neighbors of the member node component-wise. So when we add S1 and S2, we are just adding the feature vectors. We get 1, 1, 0. Then when we add that with the title node, we get 1, 1, 1. Then we add the company node, then the different job nodes J1 and J2. So we get the feature vector as 3, 4, 3, and we have 6 neighbors, right? 6 one-hop neighbors. So when we take the average, we have the mean feature vector of member M as 0.5, 0.667 and 0.5. This is simple, easy calculation. We are just calculating the mean of the member node M and its one-hop neighbors. Now let us update member nodes feature vector by combining self with the neighbor mean. We calculated the mean of the neighbors now. Now we will take 50% of the nodes on features and 50% of the influence of its neighbors to get the new embedding. So why we are doing this? As I said, we'll be having a node will be having its own feature meaning, and there will be an influence of its neighbors. So to combine its own influence and influence from the neighbors, we are doing this step by taking half of the node's own feature vector and half of the neighbor's influence, and we are calculating the new embedding. So the equation for that is new feature vector is half the feature vector of the nodes on initial feature vector and half the feature vector of the neighbor's mean. So the original feature vector of member node is 1, 0, 1. Original initial feature vector of member node is 1, 0, 1. And we already calculated the mean of the neighbors, which is 0.5, 0.667 and 0.5. Now the updated new embedding becomes half 101, which is initial feature vector, plus half the calculated neighbors mean, which is 0.75, 0.33 and 0.75. So this is the new feature vector or the new embedding of member node after one GraphSAGE layer. So in this example, we are considering only just one GraphSAGE layer for simplicity. But in actual graph, there will be multiple GraphSAGE layers and uh, multiple layers in the model. So there will be more complex learning, more complex patterns can be learned from the graph after each layer. So the next step is, now we updated node M1. The next step is to update job J1, update the node J1. So which are the immediate neighbors of J1? Neighbors of J1 are S1, S2, C1 and M. S1, S2, C1 and M. These are the immediate neighbors of J1. So let us do the same thing. Let us add the feature vectors component wise. So we are adding S1, S2, C1 and M. We get the mean as 0.75, 0.5 and 0.5. And by combining it with self, we are considering half of the influence of J1 and half the influence of J1's neighbors. So J1's initial feature vector is 0, 1, 1, and now the calculated mean of the neighbors is 0.75, 0.5 and 0.5. So we have the updated embedding or updated feature vector of J1 after first GraphSAGE layer as 0.375, 0.75 and 0.75. Now we updated nodes M1 and J1. Next step is to update job J2. So let us see which are the immediate neighbors of job J2. J2 has only two neighbors, M1 and C1. So let us add the feature vectors component wise. So we get the mean as 1, 0 and 1, 0.5. Now let us do the same thing. After calculating the neighbor's mean, let us combine it with self. We are considering the node J2's own influence and influence from the neighbors. So we get the updated feature vector of J2 as 1.5 and 0.25. So here we are computing the updated feature vector of job J2, HJ2 after GraphSAGE first layer, which is half its own initial feature vector. So half of 1, 1, 0 plus half of 1, 0 and 0.5. Here I have some issues with the font. It is half 1, 1, 0 plus half 1, 0.5. So we get the calculated mean as calculated updated feature vector as 1.5, 0.25. Now let us update the attribute nodes. Here, which are the attribute nodes? We already calculated the updated feature vectors of M1, J1, and J2. The attributes here, attribute nodes in our graph are S1, S2, T1, and C1. Let us calculate the attribute nodes updated feature vectors. So first node S1. Neighbors of S1 are M1, J1, and J2. Let us calculate the mean by adding the feature vectors component wise. So the mean becomes 0.667, 0.667, 0.667. This is simple mathematical calculation. We already computed the feature vectors for M1, J1 and J2. We are following the same steps and we are calculating the updated feature vectors of attribute nodes by first calculating the mean of the neighbors and then combining with the self node. So the mean of neighbors of S1 is 0.667, 0.667, 0.667. Now combining it with self, we get the updated feature vector of node S1 as 0.83, 0.33 and 0.33. Doing the same, let us compute the mean of neighbors of S2. S2's neighbors are M and J1. Okay, S2 is connected to M1 and J1. So maybe here there was an edge formation. That's why S2 is having neighbor nodes as M1 and J1. So let us calculate the mean. Mean becomes 0.5, 0.5 and 1. And when we combine it with self, we get the updated feature vector of S2 as 0.25, 0.75, 0.5. Similarly, we have the attribute node C1. C1's neighbors are M1 and J1. So when we do the math, we get the mean of C1 as 0.5, 0.51, and when we combine it with self, we get the updated feature vector as 0.75, 0.751. So this is simple math. Here, the only thing is we have to calculate the mean. We have to find the neighbors of that particular node. We have to find the mean of the neighbors feature vector, and then we have to combine it with self by taking 50% of the nodes on feature vectors influence and half of the neighbors influence. So this is simple math calculation. You just have to find the neighbors of the node, calculate the mean of the neighbors, and combine it with self node. Finally, we have the attribute node T1. T1's member is just M1. So we have to find the mean of neighbors. It is just M1. So M1's initial feature vector 101. And when we combine it with self, we get the feature vector as 0.501. Now we calculated the updated feature vector or updated embeddings of all the nodes in the graph. The nodes were M1, J1, J2, C1, S1, S2, and T1. Now we have the updated feature vectors of all these nodes. At this layer, every node in the graph has its new feature vector. Now let us compute the similarity scores. Similarity score between member and the two jobs. Here we considered only one GraphSAGE layer. So after the first GraphSAGE layer, we got the updated feature vectors, and now with that we are going to compute the similarity score of the member and the job nodes. So we are just calculating the dot product to find the similarity score. So the similarity score between member and job 1 is 1.093, and the similarity score of member node with job 1 node is, taking the dot product of these two, it is 1.1042. You can just use a calculator and you can compute the similarity score, and you can ensure whether my math is correct. So when we implement GraphSAGE, it is doing these things. First, in every layer, it is computing the mean of all the neighbors of a node, and then it is combining that with self, and it is updating the feature vectors, and it is computing the similarity score. This is happening at every layers of graph neural network. So this similarity score calculation, it will be happening at the final part, but all the other steps will be happening at every layer of GraphSAGE, and it will be able to learn complex patterns from the graph. Now, in this example, the similarity score between member and J1, member and J2, this is very close to each other, but this is expected. These scores are expected because we considered only single GraphSAGE layer and we assigned random initial features which does not have any meaning. But in real graph, it is not like that. We will be having different GraphSAGE layers, and in real data, after multiple layers, the network learns sharper distinctions and embeddings and encode deeper relationship across multiple hops. We will be considering 2 or 3 hops of neighbors, and we will be learning the patterns from that neighbor nodes. We will be calculating the mean of huge number of neighbors, and we will be doing the similar calculations. So this is how every GraphSAGE layer, every layer in LinkSAGE is working, and this is how LinkedIn is matching the job seekers with the recruiters. I hope this gave you a simple understanding of how LinkedIn matches job seekers with recruiters. So I'll be posting another lecture, understanding the paper's methodology, model, and result. In that paper, we will be going deep into the methodology, how this model is working, how it is encoding and uh, decoding the data, and how we are getting the output, and we will also understand the results. So I hope in this lecture you got an idea about how GraphSAGE, how link. So in this lecture, I hope you got an idea about how LinkSAGE is working and how LinkedIn matches job seekers with recruiters by performing GraphSAGE aggregation in the graph. So by understanding these concepts, reading this paper will become more easy, and you'll be getting an idea about how this is working. So see you in the next lecture where we'll be discussing the paper more detailed and we will be understanding everything. Thank you and stay tuned for more videos.